Good morning. So we're going to make a video here to introduce infinite series to you formally, and we're going to learn what it means for an infinite series to converge, and then we're going to learn a couple of ways that we can determine if an infinite series converges. So let's jump in here. So an infinite series so an infinite series is something that looks like this. Often we refer to them as an S. So it's a summation. Normally they start at n equals 1 or n equals 0, but not always. From 1 to infinity, or wherever your starting value is to infinity. And basically it's just there's some rule that determines how you get these terms. That rule is actually similar to that of a sequence. And we just add up these terms, okay? The difference between this and a sequence is we're adding up the terms rather than just listing them, okay? So just give you a couple quick little examples of what an infinite series, how it might be structured. So there's one. This could also be written like this. Sometimes you can do some algebra on infinite series and get an equivalent series, which is 2 to the n over 3 to the n. So what does this look like? This is 2/3 plus 2 squared over 3 squared plus 2 to the third over 3 to the third, 2 to the fourth over 3 to the fourth, and so on. Okay. Another one. I think this is the one I showed you the other day. I'm going to grab another marker here. This one seems to be not giving me much love. So this is 1 over n. So that's 1 plus 1/2 plus 1/3 plus 1/4, and so forth. By the way, this one actually has a name. It's called the harmonic series. For you musicians out there, at some point we might explain why it's called the harmonic series. You might actually be able to see it right now. One more for us. Just a little example, just some structure here. 1 over n squared plus 1. So we'll do some arithmetic here. So this is 1/2 plus 1/5 plus 1/10 plus 1/17, and so forth. Okay. Couple other little points of note here. So each one of these are called the terms of the series. Okay. And like this term right here, that goes with n equals 1. That term right there, that goes with n equals 2. That term right there goes with n equals 3. We'd call that the first term, second term, third term. Okay. But these terms are made up by a sequence. If we just put commas there between the terms, we would just have a sequence like we had yesterday. So the question that we have to sort of answer is, what does it mean for an infinite series to converge? Okay? Well, I'm going to kind of tell you intuitively, it means basically that when you add up an all infinite number of terms, it adds up to something. Okay? Another way of thinking about that is, as you add up more terms, the sum approaches something. Okay, so think about that. As you add up more and more terms, the answer that you get is starting to approach something. Okay, so let's look at an example here. of an infinite series that's going to converge, and what happens. Okay, so here's our infinite series. Well, let's first say what we're doing here. What does it mean for a series to converge? Okay, I better just see that. You can see that on the screen. Ah, you can't. So I'm going to scoot that down slightly. See how that looks now? Oh, whoops, I went the wrong way. You need to scoot it up, dummy. See how that looks? Probably edit all this out at some point. Yeah, that's better. Okay. What does it mean for a series to converge? So let's take a look at a specific series. 1 over n squared plus n. Okay? Which I can think of like this, just because I want you to realize that we can do algebra on these things. Okay? So let's list out some terms of this series, just for fun. You guys calculate them with me. 1/2 plus 1/6 plus 1/12 plus 1/20 plus 1/30, yada yada yada, dot dot dot. Okay, a couple of things about notation here while we're in it. Okay, this plus dot 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 here is only legal if I use this equal sign. Okay, so I have the series, this is from 1 to infinity, equals this plus dot dot dot. In fact, if I didn't have the plus dot dot and I just wrote those first 5 terms there, that would not be equal. Okay, so it's really, really important that we use good notation. Okay, all right, so what we're going to do is we're going to define something called a partial sum. Okay, that sounds really fancy. Okay, but all a partial sum is it's just summing up some of the terms. Okay, so the first one we're going to define is what we call the first partial sum, which we'll typically denote as Sn. Okay, first partial sum. Okay, what is that going to look like? Well, it's going to be the sum of the first 1 terms. So what does that look like? Well, it's just 1/2. Okay, it's pretty easy. So it's like you have all these terms listed out and you just gobble up the first one, you get 1/2. Okay, the second partial sum, which I'm going to call S2. So that's summing up from n equals 1 up to 2 of 1 over n squared plus n. Well, that's going to be 1/2 plus 1/6. So it's like I take this series, the series of all the terms listed out, and I gobble up those 2 terms, and then I add these 2 together. Okay, so I'm just going to do the arithmetic for you, just because I already did it, and there's no sense in you guys practicing your adding fractions. So the second partial sum is 2/3. Okay, so just to make sure we understand what's happening here, I add up 1 term, I get 1/2. I add up 2 terms, I get 2/3. Let's add up 3 terms, the third partial sum. One half, 1/6, 1/12. It's my best Pac-Man. Okay, so I'm going to add up 3 terms. And I get 3/4. Okay, let's do one more. The fourth partial sum. So that's going to start with n equals 1. We're going to add up 4 terms. N squared plus n. So 1/2 plus 1/6 plus 1/12 plus 1/20. And that's 4/5. Okay? So I add up 1 term, I get 1/2. I add up 2 terms, I get 2/3. I add up 3 terms, 3/4. 4 terms, 4/4. 4/5, sorry. Okay? So if I think of these numbers right here as a sequence themselves, S1, comma, S2, comma, S3, comma, S4. So S1 was 1/2, 2/3. I gotta get a new marker. Sorry. I can't live this way. 1/2, 2/3. Actually, the blue one works pretty good. 2/3, 3/4, comma, 4/5, and so forth. Okay? We're going to think of this right here as a sequence. And does this sequence converge? Another way that I could say is, if I just kept doing this arbitrarily, as far as I want, what's the kth term of this sequence? What seems to be happening here? Well, the first partial sum was 1/2. The second partial sum was 2/3. The third partial sum was 3/4. The fourth partial sum was 4/5. I'll tell you, just for fun, the fifth partial sum was 5/6. So what's the kth partial sum? What seems to be happening? Well, as I add up more terms, that sum seems to be approaching k over k plus 1. Whoa. Now I'm using k here and not n just because I've already used n somewhere else, okay? So this sequence of partial sums is approaching k over k plus 1. Does this sequence converge? And the answer is yes. If we take this limit, as k goes to infinity, we get 1. Okay? So now let's talk about what that means. What does that mean that the kth partial sum, the sequence of partial sums, or the kth partial sum is approaching 1? What does that mean? It means that as I gobble up these terms, one of them, 2 of them, 3 of them, 4 of them, 5 of them, 6 of them, that the more I do that the sum is going to approach 1. Okay? So this series that we were talking about, this original series, converges. And the reason why it converges is because its sequence of partial sums converges. Okay? The sum of this series will approach 1. Okay? So, there you go. So we're going to write that down kind of formally. A series converges if and only if its sequence of partial sums converges. Okay? Sequence converges if and only if its sequence of partial sums converges. Okay, so let's look at another example and do this with the sequence of partial sums so we can see a couple different ways. So let's take another one. So here's our series from n equals 1 to infinity of just negative 1 to the n. Okay? So if I'm going to write out some terms of this baby, negative 1 plus 1 minus 1 plus 1 minus 1 plus 1 minus 1, and so forth. Okay? So let's find the partial sums. What's the first partial sum? The sum of the first term. Negative 1. What's the second partial sum? 0. What's the third partial sum? Negative 1. What's the fourth partial sum? 0. Okay? So it seems to me that the sequence of partial sums looks like this. Negative 1, 0, negative 1, 0, negative 1, 0, and so forth. Does this sequence converge? Is that sum going to approach something? The more terms I gobble up, am I approaching something here? The answer is no. It's flip-flopping, right? So this sequence diverges. So the series diverges. Okay? And here's an example, my friends, of an infinite series whose diverges, but it doesn't add up to infinity. It just doesn't add up at all. Okay? Just because it diverges doesn't mean it's infinite. All right? All right. So let's have a drink of coffee here. Switch gears, okay? So here's the deal, friends. Calculating partial sums sucks. It's no fun, okay? Like, it's a lot of work. It's a lot of arithmetic. I chose examples, they were easy to compute. But even that last example, we had to add up those fractions. Nobody wants to do that. Computing partial sums sucks. Okay, we don't want to do that. Okay, so what we're going to do to sort of get around that is we're going to learn what I call some tests. Some tests where I can give you an infinite series like this, and you can perform a test on it. You can test it. And if it passes this test, that test will tell us whether the series converges or diverges. And different series have different tests that go with them. There are different types of series, and there are different types of tests to sort of work with the various types of series out there. Okay? So today, right now, we're going to learn 2 of those tests. All right? So let's erase the board. I told you this was going to be a lengthy video. Fast forward, I guess, if you want to. Or you can watch it in like 10 times speed or something. So here's our first test. It's called the nth term test for divergence. Okay, and I want you to underline the word divergence there. Okay? So I'm just going to state the test first, and then I'm going to show you how to use it. That's how we're going to do most of these tests. I'll state it kind of in a very formal way, and then I'll show you how to use it. Okay? So our nth term test for divergence says, okay, suppose we have a series. Okay? This is just our general thing for an infinite series. This is just like saying let f of x. Okay? This is just a general series. Okay? Here's the test, or here's the rule, or here's the shtick. If the limit as n goes to infinity of a sub n does not equal 0, the series diverges. That's it. Okay? Now let's talk about what that's saying. A sub n here, that's the little sequence that tells you how to get the terms. Okay? So we're basically saying here if the terms of your series are not approaching 0, your series diverges. Game, set, match. No chance of converging. You have no chance of whatever adding up anything if the terms aren't going to 0. Now, we sort of talked about that the other day, okay? Because we sort of crept into this idea that, hey, these were going to 0, but one seemed to be going to 0 faster than the other, okay? Now, one thing that we got to make sure we understand is this does not say that if the terms are going to 0, the series converges, okay? You can only use this to say that a series diverges, okay? What's up, friends? It is. Did you guys wear shorts today? Nice. Nice work. So Cridge and Snyder just came in. The terms of series are not going to 0. Series diverges. Okay? This test can only be used to say that a series diverges. You will never, ever, 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 ever say a series converges by the nth term test. If you do, you should be smacked. Okay? Not really. Okay, let's look at a couple examples here. Ready? Here we go. So here's our series, our infinite series. N squared plus 1 over 2n squared minus 1. Okay? I'm not even going to write out any of the terms. I don't need to. Okay? Because the first thing I'm going to do is I'm going to look at this series and I'm going to say, are the terms going to 0? So how do I determine if the terms are going to 0? I compute this limit. Okay? I compute that limit right there. That's going to tell me what the terms of the series are going to approach. Now remember, we're computing lots of limits here and they mean different things, so we've got to be able to keep that straight. In this context right here, we're computing this limit, and it's telling me what the terms of this series are doing. Okay? And if I compute this limit, I get 1/2. Guess what? Series diverges by the nth term test. Because the terms are not going to 0. All right? It's like you're adding up a bunch of terms, and then eventually the terms start approaching 1/2, and you're going to be adding up an infinite number of 1/2. Well, there's no way in the world that can converge. There's no way that's going to add up to something. It's just going to keep getting bigger and bigger and bigger. Okay? Here's another one. So how about 2n minus 1 over 3n minus 1? Okay? So let's calculate. What are the terms doing? We're going to find the limit. This n goes to infinity of 2n minus 1 over 3n minus 1. I get 2/3. Okay? What does that 2/3 mean? Okay? Don't just be like, oh, I got an answer. Okay? I got an answer there, 2/3. What does that mean? You got to know what that means. Okay? Every time you write down limit, when we're in this infinite series unit, every time you calculate a limit, you need to know why you're calculating that limit and what the result's going to tell you. What's that 2/3 mean? It means that the terms of this series are approaching 2/3. Therefore, he has no prayer. It diverges. Okay? Series diverges. Don't have to do any work. Okay? Those are the fun ones. Okay? Let's do one more nth term test. I'm just going to do it over here because I got enough room. Just so you don't have to watch me erase again. Okay, so there we go. This, you might recognize, if you don't now, you will soon, is that harmonic series. 1/2 plus 1/3 plus 1/4 plus 1/5 and so forth. Yada, yada, yada. Does this converge? Well, if we try to do the nth term test, the limit as n goes to infinity of 1 over n. And what is that answer there? 0. And what does that tell us? Nothing. This tells us nothing. Okay? It tells us nothing. All it tells me is that the terms are approaching 0, which means it might converge. It has a chance. So you're saying there's a chance. But it turns out this does diverge, and we'll learn later why. But right now, as far as our purposes are concerned with this nth term test, inconclusive. Inconclusive. Okay? Nth term test fails because the terms are going to 0. Doesn't tell you anything. All right? Now, I will tell you it does diverge, but we're going to learn why later. Okay? All right. So let's erase the board and learn another test. All right, here we go. All right. All right, here we go. Our next test, second test for today, is technically it's not a test, but I call it a test. The geometric series test. Okay, here's our next test. The geometric series test. All right? So like I said, we're going to state it formally, and then we'll do some examples. So, a series of this form, well, I forgot the word of the form. A series of the form doesn't have to start at n equals 1. That's just kind of a convention. Which, if I write out the terms of this, it's going to be a plus ar plus ar squared plus ar cubed plus ar to the 4th, and so forth. A series of this form is called a geometric series. It's geometric. Okay? Basically, a geometric series, you've seen it before. You saw it in Algebra 1. You probably talked about geometric sequences, though. A geometric series is where each term is something times the previous term. Like, for example, this term right here is r times that term. This term here is r times that term. This term here is r times that term. This term here is r times that term. Okay? And we call that thing that you're multiplying each term by, or the thing that causes you to get from one term to another, we call that the common ratio. Okay? You see geometric series or sequences all the time. In fact, a geometric sequence is sort of a discrete model of exponential growth and decay. If something is going up by 5% every year, or something is dropping by 5% every year, exponential growth and decay is geometric, okay? Except it's just the discrete model, meaning it's only like every year, not all the time, okay? You probably talked about that in Algebra 1. You should have, but you probably don't remember because it was 8th grade. All right. Here's the deal. If we've got a geometric series, okay, very simple. A geometric series converges if the absolute value of the common ratio is less than 1, okay? And it diverges if the absolute value of the common ratio is greater than or equal to 1. Okay? And interestingly enough, if you have a converging geometric series, we can actually tell you what the sum is, what it converges to. So if a geoseries converges, its sum is equal to this. The first term over 1 minus the common ratio. Okay? T1, I'm just going to say the first term. Okay? Now, maybe tomorrow, which is be Thursday for you, maybe we'll prove this, why this is true. I think it's a good exercise for us to see why this is true, but I'm not going to do that in a video. Okay? Because it's not as important, but I think it's important that you see where that came from, but I'm not going to ever have you reproduce the proof of what a geometric series converges to. Okay, so let's do some examples of geometric series and see what we got. Okay, here we go. Start off with a real easy one. Okay. Okay, so there's something that is literally in the form that I gave you. There's that a, there's r to the n minus 1. Okay? We could list out some terms if we want. We don't need to. But the first term is 3, then it's 3 times 2/3, then it's 3 times 2/3 squared, 3 times 2/3 cubed, and so forth. Okay? But if you recognize it as geometric right out of the gate, and you recognize what the common ratio is, you can just be like, oh, the common ratio, r is 2/3, so the absolute value of r is less than 1. This baby converges. Okay? And his sum, we'll go ahead and write it down, the sum of this geometric series is the first term over 1 minus r. So that's 3 over 1 minus 2/3, so that's 3 over 1/3, so that's 9. Did I do that arithmetic right? Okay, so that's a pretty straightforward one. All right, sometimes, my friends, geometric series are wearing disguises. They're wearing masks. It's like the pandemic of geometric series. They're wearing a mask, and you have to recognize them in their mask. Okay, so take a look at this. Here's one. Here we go. N equals 1 to infinity of -4 to the n plus 1 over 5 to the n minus 1. Okay? So there's an infinite series. And I'm going to tell you, my friends, this is a geometric series that's wearing a mask. Okay? We've got to unmask this thing. All right? So we're going to have to do some algebra here so that I can put it in that form. Now, you might eventually get good enough to where you recognize that as geometric right away, and you don't even have to do this step right here, but it's a little early for that. So I'm going to do some algebra here, and I'm going to say this numerator is equivalent to -4 squared times -4 to the n minus 1. Okay? Now you might think, how'd you do that? How did I figure that out? Well, I know that when I add these exponents, 2 plus n minus 1, I'm going to get n minus 1. Okay? I'm going to get n plus 1. When I add 2 and n minus 1, I'm going to get n plus 1. All right? And then I've got 5 over n minus 1. And then I can rewrite that as -4 squared times -4 fifths to the n minus 1. Okay? And now it's in that form where I have some number times the common ratio raised to the n minus 1 power. Okay? So we're going to write, hey, it's geometric. We unmask that baby. The common ratio is what? It's geo. What's the common ratio? It's -4 fifths. And, my friends, the absolute value of r is less than 1. -4 fifths has an absolute value that's less than 1. Okay? So, this baby converges. Okay, after we unmasked it, we figured out, oh, this converges. What's the sum? Okay, what's the sum of that thing? Well, it's the first term over 1 minus r. Okay, so the first term we got to go and compute. Okay, you can compute it from the way you rewrote it here, or you can compute it from the way you have it written there. It doesn't matter. But the first term, if I plug in n equals 1, I get negative 4 to the 0, 5 to the 0, so that's basically 1, so that's negative 4 squared. So the first term is 16 over 1 minus the common ratio. And yes, that negative goes in there, so that's 16 over 1 minus negative 4 fifths, or that's 16 over 1 plus 4 fifths, which is a dumb way of writing that fraction, but it's okay. So this ends up being 16 over 9 fifths. Okay, and I'm just going to leave it like, I'm just going to leave it like that. All right? So there's a geometric series that was wearing a mask. Okay, let me give you another one that's wearing a mask. Okay. This one's like wearing a mask and a face shield and a gaiter. Like, this one's really disguised. Okay, here we go. This is the longest class you guys have had all year. So here's our series. Okay, now those are decimals. Okay. And maybe you don't realize this, but what I've actually done here is I have written a repeating decimal in a weird way. This is actually 0.23 repeating. Now think about that for a second. If I add up this plus this, I'm going to get 0.2323. Then if I add this, I'm going to get 0.232323. Then I add this one on, I'm going to get 0.23232323, and so forth, okay? And it turns out, my friends, that this right here is a geometric series, okay? If I think about going from here to here, and here to here, and there to there, what's the common ratio? What did I multiply this by to get this? What did I multiply this by to get this? What did I multiply this by to get this? Hopefully you're seeing it. It's 1 over 100. Okay? The common ratio is 1 over 100, or 0.01, 1/100th. Okay? So that means that this thing converges, right? This converges. The common ratio is less than 1. So what do? The sum of this baby is going to be the first term, which is 0.23, over 1 minus the common ratio. Now 0.23 is the same as 23 over 100. 1 minus 100 is 99 over 100. That's ready to make another pot if you want. Sorry, I just had to interrupt there. And this simplifies, friends, to 23 over 99. Okay? Now, what did you just figure out, or what did we just figure out? That's how we write this fraction, or this repeating decimal as a fraction. Okay? This is a way that you can actually prove that 0.9 repeating is actually equal to 1. We can use this idea to prove that 0.9 repeating is equal to 1. I would challenge you to do that if you haven't seen that or done that before. I think Mr. Cridge might have done that with you at some point. But yeah, it is good stuff. I actually had an argument with one of my roommates in college about 0.9 repeating equaling 1. And he was actually a math ed major, and we argued about it for forever. And he's like, I just don't get that. Doesn't make sense. It can't be 1. Well, he changed his major, and now he teaches English. So how about that? So geometric series. You first have to recognize that it's a geometric series. You have to figure out what the common ratio is. Then, once you know that common ratio, is the absolute value of it less than 1, or is it greater than 1? That's going to tell you whether it converges or diverges. Okay? Then, if you're asked to find the sum, you just do the first term over 1 minus r. Simple as that, okay? But we got to remember that formula. There's going to be a lot to remember here with these series, all right? So, you've got two tests now. You have the nth term test and the geometric series test. Okay, so what you're going to do, or what I'm going to do, is on that sheet, which let me go grab. Okay, on that sheet, which is right here, okay, I'm just giving you series, and then you're going to tell me if they converge or diverge using the tests, okay? So in this top section here, if you want to pull that sheet out, I can give you a second to pull that sheet out and look at it with me. Actually, you can just pause the video. I don't have to give you any seconds. You can just hit pause and then start it back up again. But if you look at the top section, it just says verify the infinite series diverges. All four of those at the top diverge, okay? You need to figure out why. Your only option is the nth term test and the geometric series test, okay? So first determine, are the terms going to 0? If they're not, can't use the nth term test. It's probably geometric, okay? Then, number 2, Roman numeral 2, says find the sum of the converging series, okay? I will tell you, the first two of those are geometric. The third one is a trick. It's not geometric, and you can't use the nth term test. It's a trick, okay? I want to see if you can figure it out. But do that one last, okay? Do that one last after you've done the other ones, all right? 4 and 5 are repeating decimals as fractions, just like we did here. And then in the bottom section is just a melange of different problems. Like you have a whole bunch of different types of series, and you've got to perform a test on them. So you got 9 series that you've got to perform a test on. Is it use the nth term test or geometric? Okay? If it's geometric and it converges, you don't, for these problems down here, you don't actually have to find the sum. You don't have to do first term over 1 minus r. You're welcome to if you want, but you don't have to. Okay? You got to know how to do it, so if you want the practice, go ahead and do it. And I will tell you again here that one of these, number 8 is not geometric, and it's not an nth term test, okay? It's a trick, okay? So do that one last. It's like number 3, okay? Number 8 and number 3 are very similar. All right? So that's that. You might have to use L'Hopital's rule when you're doing the nth term test, so don't forget about that. So work on these problems. We will talk about them on tomorrow, and that's all. Have a great Wednesday. It's going to be beautiful. See you.